Orit Raz, and she will talk about zeros of polynomials and Cartesian products.
Okay, so thank you. Thank you for staying so late. So Avi advised me not to be too ambitious. I hope he meant in the talk. So what I'm going to do is just to introduce one very concrete problem, and I hope that through this problem I will be able to show something more general or more high level about what I do and the kind of problems I'm interested in. So first of all, let me state a theorem from 1975 of Komlosh, Sulyok, and Semeredy. And what the theorem says is that if we have a set A of n real numbers, so it is finite, then there must exist a subset A prime of size at least square root of n, such that all the differences between pairs of numbers in A prime, are distinct. So A minus B is not equal to C minus D for A, B, C, D in A prime, distinct. Okay, so this is a result, and what I would like to, the problem I would like to discuss here is a generalization of this result. So what kind of generalization? So instead of R, I would like to look at a general curve in some Euclidean space, Rd. And instead of subset of R, I want to look at, so here we had A, and what I want to look at is a subset P of gamma of points, so n points on gamma. And instead of these differences, I want to look at distances. Okay, so instead of A minus B, we will look at the distance between pair of points P and Q in P. Okay, and then I want to find a similar statement. So here is a statement, so a theorem.
Euclidean?
Sorry?
The Euclidean distance?
Yes, yes, yes. So what the theorem says that if we have such gamma constant degree, algebraic, and P of size n, so one can always find a subset of size at least n to 4 over 9, such that the pairwise distances, this is P prime, so such that the distance between P and Q is not as the distance between P prime and Q prime for every P, P prime, Q, and Q prime in this subset P prime.
So 1/2 is not true?
Sorry?
1/2 would be possible?
So I think it should be, so in general you cannot improve 1/2. I think that it should be at least 1/2, but for certain curves, the ones that are not, okay, so I believe that 1/2 should be true, but I don't know how to prove it.
So you think 1/2 should be true?
Yes.
There's
This is the short answer.
no obvious reason why that should, at least to me, doesn't look like any obvious reason why that shouldn't be true in some sense.
Why that
Why
should,
that should not be true.
okay, I agree, this is one, and at the end I will be able to say something a bit more longer answer to this question, but okay, so I would like to sketch the proof for this theorem. So what's the general approach? So proof sketch. So the general approach would be, let's take this set P of points and bound the number of quadruples. So bound of quadruples. So let's denote these quadruples as Q. So all the quadruples P, P prime, Q, and Q prime in P to the 4, such that the distance, so I'm keep writing. So the distance between P and Q is the same as the distance between p prime and q prime. And if I have a bound on the size of this set of quadruples q, then with the standard probabilistic argument, I can find a subset of subset p prime and catch relatively large subset p prime and relatively small number of quadruples q, and then throw some of the points, and then find a subset p prime which avoids q using a probabilistic. Okay, so this is the plan. You should so you should note first of all that the size of q, there's a trivial upper bound of n cubed. Okay, why? Because if I tell you three of the points p, p prime, and q, so p and q will tell me will have a certain distance r, and then I'm also given p prime. So what will be what can be q prime to have this quadruple? So I need to find q prime, which is some q prime which is of distance r from p prime and lies on the curve. So I need to look at the sphere centered at p prime, certain radius r, and look at the intersection with the curve gamma. And then there will be at most, in general, there will be at most constant number of points lying on this intersection, and they are the corresponding q prime. So n cubed is a trivial upper bound.
So gamma is an algebraic curve?
Yes, an algebraic curve, and we think of its degree as constant. And so this is a trivial upper bound, and we can still apply this method, but then we'll get something weaker. Okay, so we don't want to, we want something better than the trivial n cubed. But another thing we should note is that if, for example, gamma is a line, yes, if gamma is a line, for example, the x-axis, then it's exactly as the situation here. And in this case, we can have n cubed such quadruples. Okay, for example, if we just take, let's say all the numbers, let's say plus minus 1 to plus minus n, one can see that, and they all lie on the x-axis, on the line, then the number of such quadruples will be n cubed. Okay, so we want something better than n cubed, but we can see that in general we cannot expect to achieve it. Okay, so this we should have in mind, but let's ignore this for now and still have the goal of bounding the size of q. Okay, so my goal is to bound the size of q. So first of all, what I want to observe that this is an instance of a more general problem. And what is the more general problem? We have, let's look at this problem. We have a polynomial over the reals of 4 variables, x, y, z, and w. And I claim that this is the same as asking what is the size of the intersection of the zero set of such polynomial with a Cartesian product. Let's say with 4 distinct subsets of R. So about the size of this intersection. Okay. And why is this an instance of this problem? So I claim that a quadruple PQ, P prime, and Q prime, such that the distances are the same, can be described as a variety in R4, which is 3-dimensional, as a zero set of polynomial. Why? So note that every point on the curve, so we have this curve gamma, and every point on it has 1 degree of freedom. Yes, we can describe it in general by 1 parameter. And now if we want the 2 distances to be the same, so this is, right, we fix 3 points, let's say in general, and suppose we're given 3 points on the curve, then the distance between this will be, it's the same description of before. We will have exactly 3 degrees of freedom, and then the 4th point will be determined by the 3 first points. So the dimension is 3, and since everything here is algebraic, so we can just describe it as a 3-dimensional algebraic variety. So is this point okay? So the way I think of f is that, so f is, we have the zero set of polynomial f. And every parameter here, every value of x corresponds to a point on the curve gamma, every value of y another point. So we have 4 points on the curve gamma, and this polynomial f is 0 on this quadruple if and only if the distance between the point corresponding to x and the point corresponding to y is the same as the distance between the point corresponding to z and the point corresponding to w. So this will be this polynomial. Okay, so this is a more general question, and now I want to apply another result. So here is a theorem. So for every, so this is with Micha Sharir and Frank Dezou. So if we have such a polynomial, so two things can happen. So for every f, constant degree, so it's a polynomial for variables, one of the following holds. So one possibility would be that for every 4 sets, finite, let's say each of them is of size n, this intersection will be small. So again, the upper bound, the trivial upper bound is n cubed, so it will be much smaller than n cubed. So the zero set of f intersection with a times b times c times d is of size at most n to 8/3. So this is one possibility, and the second possibility is that the zero set of f has a certain special form. So the special form would be, so let me not write it precisely, but locally the zero set of f is of the form p of x plus q of y plus r of z plus s of w is 0, where p, q, r, s are analytic and invertible. So each of them is defined on some interval of r. So okay, so this is the general statement, and then so far everything is okay. So this is a general statement. We can apply it here, and what we conclude is that there are two possibilities. Either the number of quadruples, the size of the set Q, is bounded by this, and then we can apply the probabilistic argument and find the subset P prime, which is of this size that I stated, n to 4/9. Another possibility, we have this, and then we need to find what to do. And what we can do here, what I want to suggest to do here, is to use just the theorem of Komlosh, Sulyok, and Samoredi about subset of points on the line. Okay, so this looks pretty much the same, right? This is linear, but actually it's not precise, right? Can you see? Okay, it's not exactly the same as in the as in their theorem, because we have here different sets, so it doesn't work quite the same. This is kind of technical issue. Maybe I will. So what happens in this case? We can get something which is more concrete. The function here, this statement is about a general function f of 4 variables, but actually our function comes from something more specific, more concrete. And what we can really get here is to express, so for if we started with a curve, started with some curve, either we can bound a number of quadruples, or otherwise what one can show is that the distance, so a distance between 2 points on the curve, can be described locally as something of this form, phi of x minus phi of y. Okay, so in order to know the distance between a point on the curve corresponding to the parameter x and a point corresponding to the parameter y, we just need to compute this function. And then it really becomes, it allows us to apply this theorem for those curves who does not satisfy the theorem with the first possibility, but satisfy it with the second possibility. And then, so if one holds, we get n to 4/9, subset of size A. And if 2, we just apply this theorem, and then we get, we can find a larger set.
What does locally mean?
So it means, what's this? Okay, so it means you look at the variety. So it's a 3-dimensional variety in R4, and you can look at one point. So there is something lower dimensional that you should ignore, but other than that, you can look at every point on this, and then locally, and then there is a neighborhood, such as the intersection of the neighborhood with the surface will. Okay. So otherwise, we can find p prime of size square root of n. So sometimes we will need that. And now maybe back to your question. So here, of course, we cannot expect anything better. But in these cases, where the first property holds, then one might expect to find even larger subset. One thing that we know about these cases, about curves which, after you do all this reduction, you get something which satisfies the first property, is that you cannot put n points on, we have a curve, and you cannot, and whatever subset of n points that we choose on it, the number of distinct distances that they span is very large. We know to show at least n to the 4/3, but the common conjectures are that they span something around n squared distinct distances. And it seems like that if we have so many distinct distances, it should be easier to find a subset such that all the distances are distinct. But somehow our method gives this, which is even worse than this. So of course, on the line, we can put n points in the distinct, and there will be only n distinct distances. So, but still, this is the result.
Somehow the obvious reaction would be to try some kind of similarity trotter.
I'm sorry?
Some kind of similarity trotter for pseudo-line systems and this kind of thing. Like fixing two variables a and b, and then
You're asking about how to.
yeah, I mean where it
Okay, so good. So maybe I will say 2 more words about the proof of this general statement, right? This is what you meant. Okay, so indeed, this is what we do. We do a reduction. So we do a reduction to an incidence problem in the plane. So we have a function of 4 variables, x, y, z, w. And we look at, we are interested in the number of quadruple, the number of zeros of this polynomial. So if we look at we can fix the first 2 coordinates. For every ab in a times b, we can just look at the curve, let's say gamma ab, which is this. Okay, so this is a curve in R2, and we can look at the set of points c times d. And now we really have an incidence problem between these points and this curve, because if a point from here lies on this curve, then it exactly means that we have a 0. Right, so CD lies on gamma AB if and only if f of AB CD is 0. So this is indeed an incidence problem, which is quite standard, and bounds of the kind of Summer-Trotter do apply here, but of course we don't expect it to apply all the time because there is this other case. So we need somehow to identify the other case where the incidence bound do not work. So what will be this case? So the problem.
need a pseudo-line system.
Sorry.
You need a
Yes, you are right. So we need some conditions about the intersection of these curves. They are algebraic curves. We do have like every pair of curves intersecting a constant number of points, and we have some duality. So in general, you would expect every pair of points to be intersected by a most constant number of curves. But the thing is that this is true only if these curves are distinct. So it might happen. So one of the main challenges that one needs to deal with in order to prove this theorem is to show that to identify the case where this this curve overlap many, here we get the same curve again and again for many distinct pairs AB. Okay, so even though we change the pair AB, we just get the same curve again and again, then we cannot apply the incidence bound. So the way, so can I still 2 more minutes, right? Okay, thanks. So maybe, so just to say how we do that, so we have, so the idea is somehow to identify these coincidences, and since this is something algebraic, so we know that in general we expect coincidences either to happen drastically, to happen all the time, or to happen rarely. And so we somehow want to express this fact. And what we do, so now I'm not sure if I need to get into it, but I'll try. Avi, should I? No, seriously.
Say what you want to do next or something like that.
Not to but I really have to. Okay, so this is the main issue, and I will not tell you how it is being solved, but I'll just tell you that in order to get this special form, so we have a certain map, and okay. So what do I want to do next?
Well, I mean, you can do here's
To
the soft heart you can get for me 2 more minutes.
No, okay. Sorry, we already have.
Okay, so
What about
I'll
we open the discussion? So let's.
okay, I'll stop.